Hello guys, welcome back. So in this video, uh, we will be learning about inverse transformations, composite transformations. As an example of composite transformations, we will be learning about general two-dimensional pivot point rotation, general 2D fixed point scaling, and then apart from the basic transformations that we have seen, like scaling, translation, and rotation, we would also see a couple of other two-dimensional transformations, and then we will also see a concept called raster methods for geometric transformations. So inverse transformations. When we talk about inverse transformations, what we actually mean is inverse transformations are those transformations which will actually inverse a transformation that has been performed. For example, let us say I have an object like this and I would perform translation by adding this tx and ty, and using tx and ty, if I multiply this matrix to this object, it would move this object over here, right? Now how do I inverse it? Meaning to say, how do I get back to this place? Simple, I have to perform the same translation but in negative direction. Meaning to say, from this object I have to do minus tx and minus ty. So that's why if t is a translation matrix that I perform, the inverse of it, that is T inverse, will be the same matrix with negative tx and negative ty. Similarly, rotation. So we know about rotation that if I have an object over here, if I rotate it, say suppose by some 30-degree, I would get my object something like this, right? So this would be some, with respect to origin, if I take the angle over here, this would be some 30-degree. I'm just taking a example here. It would rotate in this direction like this. So with theta degree, if I multiply this object with R matrix, it would move by theta degree, right? Here our angle will be theta. Now how do I inverse it? Meaning to say, how do I get back this object to this position? To do that, all I have to do is, this is going in anti-clockwise direction by theta, right? So to go in negative direction, that is to in clockwise direction, our inverse would be to consider minus theta, to rotate it by minus theta. So if I, in this matrix, if I consider minus theta, I would get this matrix. So cos minus theta is cos theta, sine minus theta is minus sine theta. However, already I have minus sign here. So this would be positive sine theta. This will become a negative sine theta, and this will be cos theta. Similar to this, if we consider scaling, right? Say suppose I have a object. If I have scaled it, how do I scale it back to it original shape or original dimension? For that, take this example. I have s, x, uh, and y and 1 as my object. I'll take this. If I multiply it with this matrix, then I would get this as sx into sx, similarly y into sy, right? Now how do I get from this, how do I get my x and y back? In order to do that, I have to multiply this term with divide this term with sx and divide this term with sy. If I do this, I would get my x back. right? If I do this operation, I would get this. So if I multiply this, it would scale it by Sx and Sy to that object. If I multiply with the scaling matrix where the scaling parameter is 1 by Sx and 1 by Sy, where Sx and Sy is the original scaling parameters that I would have used, then it would inverse that scaling. So if S is the matrix which performs scaling, S inverse inverses that activity. So this is about inverse transformations. Moving forward, we'll look at composite transformations. So composite transformation is basically performing sequence of operations but using a single matrix. I'll give you an example. Say I have an object like this. I wanted to translate it and then rotate it. So I wanted this actually to be rotated by 90-degree, meaning to say I wanted it like this, right? So I have two activities. In order to get this, I would basically translate it from here to here followed by rotation, right, of 90-degree. So in order to do that, I have to take this matrix, multiply it with translation matrix, that is one matrix, and then multiply the result of that with rotation matrix, that is the second matrix. I'll have to perform two, three, how many ever transformation sequence of transformations we need, so many ever multiplications we have to go on doing it, right? Instead of doing that, what we can do is we can derive a single matrix, which is in turn derived by the component transformations that involves in this activity. For example, I am performing translation here and I am performing rotation here, right? So instead of using these matrices and multiplying these two matrices with this, I'll multiply this matrix with this matrix. The result of that I'll directly multiply with this object, and that resultant matrix will give me this result. And such matrix, which is actually derived using multiple sequence of transformations, is called as composite transformation matrix. Sometimes it is also called as concatenation of matrices. Or here, see, I have P. Let us say this is P. I have P. Assume M1 is my translation and then my rotation, right? So I should have basically multiplied P with T and then the result of these two multiplication with R in order to get my translated object. Instead of this, what I can do is I can multiply these two, the result of this, let's call it as M, and multiply M with P. So directly you will get P dash. So this is composite transformation. It involves basically a sequence of transformations, but that would be done using a single matrix. As an example to this, let's see general two-dimensional pivot point rotation. Now you see, we have already seen in rotation that if I have an object here, if I wanted to, rotate it by 90-degree, it would go somewhere over here. It's like this. If I take the axis, it would be 90-degree. So basically it's spinning around the axis, right? What if I don't want that? What if I have a triangle here? I don't want it to rotate. If I multiply with the rotation matrix with theta is equal to 90-degree, it would bring my object somewhere here, 90-degree, right? I don't want that. What if I wanted it to rotate it with respect to this point, not with respect to origin, meaning to say over here it should have 90-degree, the rotated object. My result should look something like this. What if I wanted to do that? So this point of reference what we take, that is called as pivot point, right? Now this operation is also called as rotation around fixed point. It is also called as rotation around pivot point or pivot point rotation or fixed point rotation. All these are alternative names that you get to hear, right? So I'll give you an example. This can be achieved basically. See, so far we know only one matrix that would rotate the object around the origin. We don't know how to rotate it with respect to a fixed point, but we know how to rotate the object with respect to origin, right? What if I bring this object to origin and then rotate it? I'll show you an example. Say this is my triangle. My point of reference for me is XR and YR. Now I want to rotate it, this object around this point with 90°. I want it something like this. Right? So I don't want, if I rotate it around origin, it would go somewhere like this. So something like this out of the screen with respect to this coordinate frame that we have taken. I don't want that. I want it to rotate it around this fixed point. In order to do that, what I'll do is I'll perform translation such a way that I'll make this point come and sit on the origin over here like this. To do that, what I'll do is, since this is xr comma yr, if I want to make this point as 0 comma 0, I have to bring this object or subtract this all the points on this object with xr minus yr. So that would bring the object such a way that xr and yr will come and sit at 0 comma 0. So that means I have to perform translation of minus xr and minus yr. Once I do this, I'll apply r theta. R theta is nothing but my normal rotation matrix that I know. Cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. The three-dimensional rotation matrix what we have discussed, that is the matrix that I multiply with this object. Once I do this, since this is in the origin, it just rotates here. Though it is rotate here, this rotation is still happening around the origin only. But since the object is already at the origin, it is getting rotated over here like this. Now what I'll do is I'll move back my object to its original position. So to do that, what I have to do is I have to add XR and YR back to all these points. That means I'll translate this object back to XR and YR. If you see, we got the result that we expected. So this is a composite operation. Now in this composite operation, we involve translation activity, negative translation, and then we involve, a rotation activity, and then a positive translation activity. So this are the three steps that we would follow. So the sequence would be translate, rotate, and translate operation. So what we'll do is, if XR and YR is our pivot point, we translate the object such a way that pivot point position is moved to coordinate origin. Then we rotate it with respect to origin, and then we move it back to its original position, as I explained in this example. Concatenating the matrices for these three operations produces the following matrix. So see here, I have the first operation to be performed is negative translation, then I have to perform rotation, then I have to perform positive translation. So to perform negative translation, what I will do, this is the matrix minus XR and this is rotation matrix, this is translation matrix. So here one thing we have to remember, we have to move, these operations are performed from right to left, not from left to right. Usually how we do, we have to go from right to left, meaning to say first multiply this matrix with this matrix, the result of that you multiply this matrix. So multiplication of these two matrices you have to do. from this matrix with this matrix, the result of that, this matrix is multiplied with the result of these two multiplications, and what we would get is this matrix. Again, the order in which we multiply is very important. Since matrix multiplication is not commutative, we have to be very careful about the order in which we multiply. Now rotation around pivot point is given by this notation. So normal rotation is given by r of theta. This we don't have to give any point here because this is rotation around origin, but over here we give the reference point or the pivot point, whatever we are considering in this rotation, right? So if you see, this is the added term. This term is the term which actually represents translation, positive and negative translation. And this term, these four terms are rotation terms. And these two terms, if you remember, in translation only these two terms are the one that gives us parameters for moving the object, right? Similarly, this is composite term which gives us x-axis translation, both going to negative x-axis and then going back to positive x-axis, moving back to its original position, going to origin, moving back to its original position. That is given by these two parameters in this matrix. So moving forward, general two-dimensional fixed point scaling. Now, if you guys remember in our scaling video, we had discussed that if I have an object, something like this, if I scale it down, meaning to say if my scaling factor is less than 1, then it moves towards the origin, right? We had also discussed an example. We had taken, I think, 0.5 as an example of scaling factor, and we were able to scale the line towards the origin like this. So if we are scaling up or increasing the size, we move away from the origin, something of this sort, right? So basically we move towards the origin or move away from the origin depending on the scaling factor being less than 1 or greater than 1. Now what if I don't want that? Even over here we have this origin as some kind of reference, right? What if I don't want that? What if I want to scale the object with respect to this line only? Or say suppose I want over here, I want my object if I scale down, I want my object to come over here. If I scale up, I want my object to come over here itself. What if I want that? Right? Over here we are considering this point as our point of reference. In this example, as I am showing, we have XR and XF and YF. Say suppose this is our XF and YF. It's similar to our rotation around pivot point, even the fixed point scaling. What we do is we move it back to origin. So we do minus XF, T of minus XF and YF, minus YF. And then we apply scaling with scaling factors Sx and Sy. It might increase the size or decrease the size. It doesn't matter depending on if it's greater than 1 or less than 1. And then we move it back to its original position. So the matrix of that would look something like this. So negative translation followed by scaling followed by positive translation. This is negative translation matrix, scaling matrix, positive translation matrix. The result that I would get is this. Again, these two terms are giving me the scaling activity in the composite operation. These two terms gives me movement of movement towards the origin and going back to its original position. Again here the order we have to be very careful. We have to multiply this matrix with this matrix first, and then this matrix is multiplied with the result of it. We have to be very careful on that. We go from right to left. Now moving forward, the transformations that we discussed so far, translation, scaling, and rotation, they are called basics transformation activities. Now, do we have any other transformations that we can perform? Yes, we do have. There are two transformations additionally that we can discuss. One is called as reflection, and the other one is called as shear. Now, reflection. What this reflection does is it just inverses this object mirror image. It produces the mirror image of that object with respect to some reference line. Over here we have taken this x-axis, that is at, the line at y is equal to 0 as the reference for mirroring. Now shear, we will discuss shear in detail in the coming up slides. We'll first look into reflection. Shear. So reflection produces mirror image of an object. Now this is generated relative to the axis of reflection. So this is something equal to rotating the object by somewhere around 180 degree. Yeah, exactly by 180 degree. So reflection at y is equal to 0 line, so that is x-axis. This can be accomplished using this matrix. This is reflection matrix for reflecting the object over line y is equal to 0 or over x-axis. So if you see here, the x-axis values you're not changing, only the y-axis values you want to change. And what exactly will they be? You want this 2 to be minus 2. It's not actually the coordinate position. They are the points that have been given, numbers, names that have been given to these vertices. Assume that this was 2 comma 2. In that case, the x-axis will be 2 and this 2 will become minus 2. So basically you just want to inverse the y coordinate values. That's it, right? So for that, what you will do is assume that there is a point x, y and 1. Multiply this with this, you would still get x. Multiply this with this, you would get minus y and 1. So the result of this multiplication of this matrix with any object produces the object with minus y, right? So that's the effect of it. So all these points becomes minus y and this will be the reflected object. So this is reflection along line x is equal to 0. Over here, our y values remains the same. These values, whatever we have, this remains the same. But let us say this is the original position that we have. These negative values should become positive. If this was our original object, then the positive value of x should become negative. Basically, the sign of x should become negative. So only x values we are negating, the y values we are keeping the same here. So this is the reflection matrix for reflection over x-axis. So this flips both x and y values. So meaning to say this reflects along this line, the line that passes through the origin. This 2, if assume this is 2 comma 2, this becomes minus 2 comma minus 2. So both x and y are inversed. So this is reflection with with respect to this line. So moving forward, we have shearing. So shearing, what shearing does is, assume that our object is actually made up of layers, something like this, and you are shearing with respect to this line on which the object is sitting, right? Now what you will do is, you will see how far this layer is with this line. It's on the line, so you won't move it. However, this layer is actually a little above or little away from this reference line that we have taken, right? So what you will do is, so you will keep the object as it is like this at the first layer. This above layer, you will move it a little bit towards the positive x-axis. So how much you will move, that will be proportional to how far this is with respect to this line of reference, and there is something called a shearing parameter. So that shearing parameter also defines how far you move it. So there are two things: how much you have to move is depending on shearing parameter and how far it is from the line of reference. Now say suppose the next layer is little more away from the x-axis, so you move a little the next layer, so like this. So that's what the object would look something like this. This kind of square would look some tilted parallelogram. See, this is what has been explained here. The shape appears as if the object were composed of internal layers that had been caused to slide over each other. So that's how this sliding has been, you can note this sliding effect over here. So the two common shearing transformations are shift the coordinate x values or the y values. Now see here, this is an example of shearing with respect to x direction. Now we are shearing over x axis with reference line as y is equal to 0 and shearing parameter is 2. So what you will do, since at y is equal to 0, all these points in the object, there is the is at y is equal to 0, you will not move that layer. So the next point, let us say somewhere here, the point over here, there is some amount of distance here, right? So how much ever this distance is, considering that and the shearing factor of 2, you are going to move all the points of this layer by this amount. So similarly over here, this layer is the farthest with y is equal to 0. So this layer moves the most. If you see, this layer has moved the most actually. So here x value was 0, but here x value became 2. The y value is not changed. Y values are all the points still remain the same. Only the x value are changing with the sliding effect. So we'll see the formula how this has been taken place. Since it's in x direction, the x value is added with the shearing factor into how far that y, so that point's y, how far is that from the reference line. So reference line that we have taken is y itself, right? That is the y0. So since y is equal to 0, whatever the y value is, that itself gives us this gap. So we have taken y directly here. So in order to achieve this, this is the matrix that defines shearing in x direction. So SHX, this factor gets multiplied by, so this assume we have XYZ, XY1 here. So the first row, X, Y and 1. So if I multiply this, I have X and then plus this Y into SHX into y is what I get, right? Plus 0. So this 0 into 1 is 0 is what I get. The next point that I would get will be y. So that is y dash is equal to y, and my 1 remains same. So this will be the resultant result that it will be give, that this matrix operation will give if you perform this sharing operation. Similar to this, the y direction also can be done. So with respect to y direction, if you do, x dash will be x, but y dash will be y plus shy into x. So that it's the same effect. Instead of moving like this, we would tilt the object like this. So y with that is with respect to line x is equal to 0. That is the y-axis line. So with this line, if we do now the shearing. Now over here what we did was we saw with respect to line y is equal to 0 and x is equal to 0. That is the axis lines itself. So now what if I wanted to shear it with some other reference line? That also we can do. Let us say I want to shear it with line y is equal to yref is equal to -1. Earlier we did at yref is equal to 0, right? Now, so this layer earlier did not move in x direction. It was still the same. However, if you see here, it has moved. The reason is there is some kind of offset with the reference line, right? So we have to take that into consideration. So this distance also we have to do. So in order to do that, this y value only gives us this distance, but we want this distance. So we want to multiply this distance with the shearing factor. So this will be the equation that we would get, shx into y minus yref, and the matrix, if we want to convert this into matrix operation, this will be the matrix that we would get. So this row multiplying with x, y and 1 will give us x plus shx into y minus shx into yref. Taking shx common, we would get shx into y minus yref. So this is with respect to x as a in y direction, x as a reference as x ref is equal to -1. So similar to our y axis, y values, we would do considering this distance. So x minus x ref, and this is the matrix that defines shearing with respect to y direction over some other reference line, not over y is equal to 0. So moving forward, raster method for geometric transformations. Now, as we had already discussed, raster methods, uh, raster based system, meaning to say, all the objects are represented in terms of pixels in frame buffer. Everything we consider as graphics are actually results of values in frame buffer, which are considered as pixels. Now, can I achieve this using raster manipulation, that is directly manipulating the frame buffer? Can I achieve any of the geometric transformations? Yes, we can achieve some geometric transformations, not everything. So far what we have done is all the transformations that we have done, we have considered our object as geometric entity, and we perform some kind of mathematical operation over that geometric entity, and we got the result. But what if we want to manipulate the pixels directly the frame buffer values? If at the memory level, if we change the content, can we achieve geometric transformations? Yes, we can, but not all transformations we can achieve it. Some kind of complexity would involve as and when we move towards complex transformations, when we have to directly manipulate the pixels. To deal with simple transformations, yes, we can directly manipulate pixels, and that in fact gives us faster result, right? So alternative method for performing this using raster system, these two are similar, two things that you have to know. The function which manipulate the rectangular pixel array are called as raster operations, and moving a block of pixels. So let us say we have block of pixels over here like this. If you want to move this set of pixels to somewhere else, then we call that operation as block transfer, moving it like this. Now we will see what all operations we can do. Yeah. Say, suppose this is the translation that we have, right? What we can do is we can consider the frame buffer area around this object, some kind of this area. We wanted to translate, initially our problem would be to translate this object to somewhere here. In that case, what we'll do is we'll select some area and we will copy the pixels in that area into the area that we want. And in order to remove this image over here, what we can do is we can select the background color and we can flood those colors in all these pixels in the frame buffer. I am talking here at the direct pixel level, in the frame buffer level. In the memory we can do that. So whatever the value that would present in this pixel, we can move it to this pixel. So we can go on doing that, and that would move our object. After that, we go back to this pixel and color it or put the value of the background color in this, and that would give us the object over here instead of it being over here. That also we can perform using pixels directly. So if you notice, this is nothing but translation, and we achieve translation using direct pixel manipulations in the system. Even rotation can be performed. If you see here, this is rotation. Say suppose this was your frame buffer values. These define your object colors, the values in the pixel positions. Let us say this is your object. Basically you wanted to rotate it by 90°. Then what you would do is you would do an activity of transposing the matrix. So you have converted this column into, sorry, this row into this column, and the second row into second column, third row into third column, and the fourth row into fourth column. So let us say if our object was something like this would rotate the object to something like this. Though the object that has been taken here is in the shape of a square, I am narrating it you this with a picture of triangle. Okay, so please do not get confused with it. Now what if I wanted to rotate it further? What if I wanted 180°? Then what I would do is I would do something like this. Again, this column is converted into a row. Now if you see, this complete row has been converted into the first row, and you're reversing the positions of the values inside that matrix also. So this would actually give us something like this. So that's what happened, no? The last row has become first row, and this position, in this example, take this was 12, it would be over here. So 12 is in the first position. So that also we can do. Even the scaling we can perform. Let us say this is the picture that I want to scale it over here. What I can do is say if this is the pixel, I want to scale it with SX as 2 and SY as 2. Then what I'll do is I'll go on doubling the pixel. This pixel color I will, put it in these objects. So whatever the pixel color was there over here, I would put it into something like this. So I'll go on doing this, and I will I'll be able to scale it. Let us say there was a object over here and all these colors was something I wanted to scale it. In that case, I can reduce the 4 pixels into single pixel. What if the colors were different in these 4 pixels? I can take weighted average, or I can average the color, or I can basically take some color by interpolating, something like that I can do, and I can fill in this color. So and that would give us the scaling. This is again using direct pixel manipulation. Now, the raster methods, how to do, we discussed. But what are the OpenGL functions that we would use? So before even we go into the OpenGL functions, we will look at this specific function called as GL raster position. The star is basically, it can be 2f, f or 2i. This gives us the data type, and this gives us the number of parameters. Now 30 comma 40, if I pass here, this 2f or 2i, whatever is, it is similar to what we had represented in GL vertex 2i or 2f in our examples that we had seen earlier in CG classes. This 30 and 40 would mean the x and y value of the pixel that we are talking about. So the current pixel in the frame buffer would be set to 30 and 40. Whatever manipulation you do in the frame buffer, that would be applicable at the pixel at 30 cross 40 position, whatever we would have. Imagine again the frame buffer as a two-dimensional array, and at position 30 cross 40, 30 comma 40, it would go and do that operation. If you want to put a color there, it would go and put a color in 30 comma 40. This raster position will actually help us to set current position in our frame buffer. This is similar to our cursor in the documents that we would do. For example, in Notepad, if I set my cursor in a sentence, if I set my cursor somewhere, and whatever I type would appear in that position of the cursor, right? Something like that. Whatever I do in my frame buffer, that would be applicable at the current position of the uh, frame buffer, and that current position can be set using GL raster position. Now, GL copy pixel. Copy pixel is a function which actually starts this is the initial position of the block that we would like to copy. Let us say I wanted to copy this block somewhere over here. Then I would set my GL raster position to this pixel, and then in copy pixel I would give this this position, pixel position, as xmin and ymin, and then I would give my width and height of this block, and I would tell that GL color are the values. This is a OpenGL constant which tells that RGB values or the color values I would be copying from the frame buffer. So what it does, copy pixel, what it does is it copies from this position, that is from this position, with given amount of width and height, this block, the color values will be copied to the current raster position. So the current raster position, this width and height will be copied as it is. So this is, using this we can achieve translation. Now, GL read pixels. What GL read pixels does is, GL read pixels helps us to, read the pixel values, a block of pixel values from frame buffer, and into a data structure in our programming language. Probably you can consider it as an array. You want to read a block of pixel values into an array, then you'd use read pixels. Similarly, draw pixels, if say suppose you had some color values in an array and you wanted to put it at a certain position in your frame buffer, then you would use draw pixels. So why are these important? Why? Because I told you the rotation is nothing but transposing a matrix, right? So scaling also you can correlate it to some kind of matrix manipulation or array manipulation. You can achieve this transpose and everything using an array. What you can do using read pixels is from xmin and ymin, that is the initial left bottom position of the block that you want to start, width and height you will take the RGB values of data type unsigned byte. This block, let us say, is copied into a user defined array called as color array. This is a user defined array name. Now color array would be basically, you know, after this function execution, it would be a two-dimensional array which would have all the pixel values of whatever the values were there in this block. So this would be copied. Now using your programming language, you can perform transpose or multiplying the matrix with whatever it is, or copying the matrix, or increasing the size of the matrix, and whatever you wanted to do, you can do that. Once this matrix is ready with the values of the transformation that you wanted to do, you can put it back into the frame buffer, and it using GL draw pixel. GL draw pixel again puts it at a position of current raster position in the frame buffer. Here you are giving width and height. So of this array, how much you're doing, the color values and data types are the values that you're putting, and the values are present in color array. The content of color array is copied into the current raster position of size, width and height in the frame buffer. So this guys are the OpenGL raster functions that we would use in order to perform raster transformations or pixel level geometric transformations also. You would have by now noticed that it would be difficult to perform, or it would be a little complex to perform rotations, probably with some degree, some other degree apart from 90 degree or 180 degree, say suppose 10 degree or 20 degree. The kind of matrix manipulation that we would want to do would be quite uh, tiresome or quite complex. So this method has its limitation. However, it also has its own advantages. On certain transformations, directly operating at memory level would give us faster results. So that's one thing that we can note. So that's about it.